Hey everyone, welcome back for another deep dive. This time, we're looking at something that you sent in.
Oh, excellent.
Yeah, it looks really interesting. It's all about turning carbon dioxide into carbon monoxide. And,
It sounds simple.
on the surface it does,
Right.
but it's got some really cool implications for a greener future. Like I was reading through this and I was like, wow, this could actually,
It could
be a big deal.
Yeah, this is really exciting research.
Yeah.
Because it's addressing a huge challenge that we have, which is how to make CO2 reduction more efficient. And we're not just talking about small improvement. We're talking about transforming a greenhouse gas into a valuable chemical building block. And they've found a way to do it with amazing precision.
Okay, now,
Okay.
I got to admit, when I first saw the title, it's CO2 to CO. We're like, okay,
Yeah.
chemistry,
Right.
but why is this so cool?
Why should we care?
Yeah, exactly.
Think of carbon monoxide as like a molecular Lego brick. You can use it to make a ton of things, from plastics to fuels. So instead of CO2 just being this climate change villain, we can turn it into something super useful.
So we're taking something bad
Yeah.
and turning it into something good. I love. Okay, but how are they actually doing this?
All right, so they're using these things called silver nanoparticles.
Okay,
Tiny, tiny particles of silver.
I've heard of those.
Yeah, you probably have. They're already pretty good at this CO2 to CO conversion.
Okay,
But the researchers in this paper wanted to take it to the next
of
level.
course they did.
Okay.
Gotta push the boundaries.
So how did they do that?
Yeah. How?
Well, they used this special molecule called 3-mercapto-1-picture-204-triazole.
Oh boy, that's a mouthful.
Right. It's a lot easier to just call it M-Triz.
Okay, M-Triz.
So basically, it's like giving these silver nanoparticles a special suit that makes them even better at their job.
Okay, so M-Triz.
Mm-hmm.
It's like the silver sidekick.
Yeah.
Helping it out.
I like that analogy.
Yeah.
Yeah. And the results are seriously impressive. They achieved a Faradaic efficiency of 99.2%, meaning that almost all the electricity used in the process actually goes towards making CO.
Now hold on. Faradaic efficiency. That's not a term I hear every day. So is that like a measure of how good the process is?
Exactly. It tells us how much the energy we put in actually gets used to make what we want, and 99.2% is incredibly efficient.
Wow.
Yeah.
Okay, so
It's efficient.
it is. They also saw high current density too, right?
Yes, they did, which means that the reaction's happening quickly.
Okay, so this new catalyst
Yeah.
is efficient and speedy.
Yes.
Color me impressed.
Yeah.
But I'm still curious about
Yeah.
how does this M-Triz
Yeah.
actually work its magic?
Okay, so they did a whole bunch of tests, including some really high-tech ones that let them actually watch the reaction happening in real time at a molecular level.
Whoa.
Yeah. Pretty cool stuff. So basically, they found that the M-Triz enhances CO2 adsorption.
Absorption.
So that means the CO2 sticks to the silver catalyst better.
Oh, okay. So it's like M-Triz is a magnet for CO2, pulling it in.
You got it. And not only that, M-Triz also lowers the energy barrier for the reaction. You can think of it like greasing the wheels, making the whole process run more smoothly.
So M-Triz is not just a magnet, it's like a super efficient chaperone, making sure the CO2 and the silver get together and do their thing.
I like it.
I'm full of analogies today. But what about the other players in this reaction?
Yeah.
Didn't they use a special electrolyte too?
Yes, they did. They used an ionic liquid, which is kind of like a liquid salt. And it turns out to be way better at dissolving CO2 than a traditional electrolyte.
So it's like creating a CO2-rich environment, making it easier for the reaction to happen.
Exactly.
And when they compared this new setup to a traditional one, what happened?
Oh, the results were crystal clear. The M-Triz and the ionic liquid together just supercharged the process, made it way more efficient.
Teamwork at its finest. But even with a superstar team, there's always challenges, right?
Oh, of course. You're absolutely right. One challenge they're working on is long-term stability. The catalyst performance does decrease over time.
Ah, so like a marathon runner hitting a wall.
Yeah.
Makes sense. Nothing's perfect right out of the gate. But even with that challenge, this research feels like a big step forward.
Absolutely. And it opens up so many questions, like what if we could find other molecular sidekicks like M-Triz that could boost different chemical reactions?
That's what I'm talking about, is like a whole new world of possibilities. But before we get too carried away, let's stick with this amazing silver and M-Triz duo. What else did they discover about how well it works?
Well, they did some interesting comparisons. With silver sulfide, they found that silver sulfide also shows some activity in CO2 reduction, but it's nowhere near as efficient as the silver with the M-Triz.
So it's not just about having any old silver catalyst or any sulfur compound for that matter. It's the M-Triz that's the real game changer here.
Precisely. It really highlights how special M-Triz is in this whole process.
Okay, I'm sold on M-Triz being awesome.
Yeah.
But let's go back to that special electrolyte for a second. You mentioned it was like a liquid salt. Can you tell me a bit more about that?
Sure, so it's called an ionic liquid, and it's made up of ions, kind of like the electrolytes you find in sports drinks. But unlike the stuff that athletes drink, this ionic liquid has a super high solubility for CO2.
So it's like creating a CO2-packed party in there, making it much easier for the reaction to happen.
You got it. And the specific ionic liquid they used in this study, it's called BMIMPF6, and it's been a star performer in other CO2 reduction studies too.
Interesting. So they didn't just use the ionic liquid on its own, though, right?
No, they mixed it with acetonitrile and a bit of water.
What do those do?
The acetonitrile helps everything mix together nicely, and the water helps with some of the chemistry steps in the reaction.
So it's all about creating the perfect environment for the CO2 conversion to happen. Makes me wonder, what if we tweak the recipe a bit? Could we make the reaction even better?
That's a great question. And it's something that researchers are definitely exploring. But even with this specific mix, the difference is clear. When they compared their ionic liquid electrolyte to a traditional one, the results were night and day.
No contest. So we have our silver catalyst, our M-Triz wingman, and our super electrolyte, dream team assembled.
Yeah.
But you mentioned earlier that there were some challenges too, especially with keeping this reaction going strong over time.
Yeah, that's right. One of the main hurdles is the long-term stability of the catalyst. They noticed that over time, the rate of CO production slowed down.
So even the best teams can get tired.
Pretty much.
What's causing this slowdown?
Well, they did some detective work, and they found that some of those M-Triz molecules were actually detaching from the silver surface over time.
So the wingman is getting a little burnt out and taking a break.
You could say that. And this loss of M-Triz seems to be the main reason why the performance drops.
Okay, that makes sense. But even with the stability issue, this research is still pretty groundbreaking. It shows us that we can really boost CO2 reduction by carefully designing the catalyst and its environment.
I couldn't agree more. It really opens the door to so many possibilities for sustainable chemistry.
And here's where it gets really interesting. We could potentially use this approach to tackle other chemical reactions too, right?
Yeah.
Not just CO2 reduction.
Absolutely. Imagine being able to create catalysts that can break down pollutants, produce new materials, or even make medicines with way less waste and energy.
It's like a whole new toolbox for chemists.
Yeah.
But speaking of tools, you mentioned earlier that the researchers use some pretty high-tech methods to figure out how this catalyst works at a molecular level.
Oh, yeah, they went all out. They used computer simulations called density functional theory, or DFT, to model how the different molecules interact.
DFT sounds intense.
It is. But think of it like a virtual chemistry lab. They can run experiments and test things out on the computer before doing them in real life. And in this case, the DFT calculations really help them understand why adding M-Triz makes the catalyst so much better at grabbing CO2 and turning it into CO.
So they're getting a sneak peek into the molecular world.
Yeah.
Pretty cool. But they didn't just rely on computer models, did they?
Nope. They also used a technique called in situ atr-seros, which basically lets them watch the reaction happening in real time, right on the surface of the catalyst.
So they can actually see those molecules in action.
Exactly. And what they saw confirmed what the computer models predicted. M-Triz was doing its job beautifully.
That's amazing. So they've got the computer simulations and the real-time observations, all pointing to the same conclusion. It's like having two witnesses confirming the same story. But I have one more question about this particular study. They compared their M-Triz silver catalyst to a few other setups, right? Like plain silver and that silver sulfide. Why was that so important?
Those comparisons were crucial because they allowed the researchers to isolate the impact of M-Triz. By comparing the performance of the different catalysts, they could definitely show that M-Triz was the key ingredient for that incredible boost in efficiency.
So it's not just about having any silver catalyst.
Yeah.
Or any sulfur compound. It's the M-Triz that's the secret sauce.
Exactly. It really highlights the power of careful molecular design.
All right. I think we've done a pretty thorough job of unpacking this research. We've talked about the key findings, the hows, and even some of the challenges that lie ahead.
I agree. We've covered a lot of ground.
But the story doesn't end here, right? This research has implications that go way beyond just this one study.
You're right. This is just the beginning.
Okay, now I'm really intrigued. What kind of ripple effects are we talking about here? Where does this research lead us next?
Well, for one thing, think about the potential impact on sustainability and green chemistry.
So we've been talking about this amazing research using silver nanoparticles and M-Triz to turn CO2 into CO. And you're saying this is just the tip of the iceberg when it comes to sustainability.
Absolutely. This research gives us a blueprint for designing catalysts that are incredibly selective and efficient. And that's not just good news for CO2 reduction, it's good news for all kinds of chemical processes.
Okay, so we're not just talking about making fuels and plastics from CO2.
Yeah.
What other applications are we talking about here?
Think about it. What if we could use this approach to break down pollutants in the environment, or create new materials with less waste, or even manufacture medicines more efficiently?
Wow, that would be incredible. So this tiny tweak at the molecular level could have huge ripple effects across entire industries.
Exactly. And it's not just about making existing processes more sustainable. We could also use the strategy to invent entirely new chemical reactions that were never possible before.
Now we're talking, so what kind of new reactions are you envisioning?
Well, for starters, we could explore using CO2 as a building block for all sorts of complex molecules. Imagine creating new polymers, fuels, or even pharmaceuticals directly from this abundant greenhouse gas.
That sounds like science fiction. We could literally turn a problem into a solution.
Yeah.
But let's get back to reality for a second. We talked about this catalyst stability issue earlier.
Mm.
How do we make sure this technology is reliable enough for real-world applications?
That's a great question, and researchers are already working on solutions. One idea is to find new ways to attach the MOTRIS to the silver, making a stronger bond that's less likely to break.
So it's like finding a super glue for molecules.
Exactly. Or we could even tweak the MOTRIS molecule itself, making it more resistant to wear and tear.
It sounds like there are tons of possibilities here. It's like a whole new field of research has opened up.
I couldn't agree more, and it all stems from this fundamental breakthrough in our understanding of how catalysts work at the molecular level.
So this research isn't just about making cool new stuff. It's about pushing the boundaries of chemistry itself.
Exactly, and who knows what amazing discoveries are still waiting to be made. It's a pretty exciting time to be a chemist.
I can definitely see that. But before we wrap up this deep dive, I want to leave our listeners with a final thought. If you could dream up the ideal next step in this research, what would it be?
What if we could create a system that uses sunlight to power the CO2 reduction process? Imagine capturing CO2 from the air and turning it into valuable products using renewable energy. Talk about a game changer.
It's an amazing vision. It's so inspiring to think about the potential for a greener and more sustainable future. And who knows, maybe one of our listeners will be the one to make that vision a reality. Thanks for joining us on this incredible deep dive. Keep exploring, keep questioning, and keep learning.